Good evening, everyone. So today we'll start the 11th lecture of stochastic process. So today we will actually uh, uh, today we'll actually discuss about recurrence and transients. In discrete in Markov chains. So first, let me just give a what we did last time. So in the last time we discussed discrete and Markov chains. We saw some examples of discrete and Markov chain. One was Bernoulli process, then simple random walk, which we made it as a gambling experiment. Then we saw Ehrenfest earn. Then we calculated how to do multi-step transition probabilities, which we also saw in the last class. Then we gave Chapman-Kolmogorov equations and communicating classes. Then we read about equivalence relations. What are the three properties that a relation need to satisfy for it to make an equivalence relation? So first one's reflexivity, then symmetry, and then transitivity. So and we showed that communication is an equivalence class. And then we defined definitions of irreducibility and periodicity. So today we will talk about recurrence and transients. So before we talk about recurrence and transients, I'll put down some notations that will convenient for us. So from next time we will use those notations. So if I say EI of some event A, which implies probability of the event A given x0 equal to I. Similarly, if I say expectation I of an event of a random variable x, then it is expectation of x given x0 equal to. Hmm. So what does this two mean? This two means that if I write E I xn equal to j, the event A, I am replacing it with xn equal to j. This basically means probability of xn equal to j given xi equal to x0 equal to I. Which is basically the n-step transition from I to j. N-step transition probability. So okay, this is clear. Next we have ni. We call this the number of times xn equal to I. So this is basically the total number of times the Markov chain heat side. So how many times the state takes the value xn equal to I. And here we do not count the time zero. So at first step where it has that we have not count. So now this is also a random variable because it can hit a random number of times once you have started DTMC. So now this is one thing. The next thing is Fij. Fij return, I define it as the return probability. So return probability from I to j. So Fij is formally defined as probability of xn equal to j for some n greater than or equal to 1, condition on that you are starting from I. So what it means that Fij is a probability. If you're starting from I, condition on that you're starting from I, then what is the probability that you will eventually visit j at least once? So basically what this says is this is equal to probability I. So this is the conditioning on that you're starting at A. And the number of times you visit at least once means it could be more than one, but you at least visit once. So nj is greater than or equal to 1. So now the complementary probability for this is u2. So Fij is the probability of return from I to j. 1 minus Fij is probability of no state is j for all n greater than or equal to 1, given that you're starting from I. Now, so suppose I want to calculate the probability of condition that I've started at I. Chain will eventually visit j, and then eventually visit k. This, so what this means is, so you start at I, and what is the probability that you eventually visit j? So you have that probability as Fij. And then what you're doing is now you're starting at j, because now once you've reached j, you don't need the history. This comes from Markovity. So if you start at j, what is the eventuality that you visit k? So fjk. So you can multiply these things because of the Markovity property that we have seen before. So now we can write of going from I, starting at I, condition that you're starting at I. What is that probability that I visit I more than two number of times? So what it is saying is you have state I, you start at I, you go to different states, you come back to here. Once you come back here, the ni is equal to 1. Then you visit different states. Then again you come back. From here, you have ni equal to 2. And you want the probability of this happening. So this what it means that you start from state I, reach state I. This probability is Fii. Again you start from state I. Now you this doesn't matter because of Markovity. You can again write the probability of going from I to I again as Fii. So the total probability of you hitting I twice or at least twice is Fii whole square. Okay. Similarly, you start from I, ni greater than or equal to 3. Fia whole cube. And more generally, if you start from I and then I greater than or equal to k is equal to Fia whole power k. Similarly, if you want Pi, but now Nj greater than or equal to k. So what that means that you start at, so you have I and you have j, two different states. You start at I, you hit j. This is Nj equal to 1. And then you go back and this is Nj equal to 2. And then Nj equal to 3. So on. You would continue this until you hit k times. This first one would be Fij, but the second one would be Fjj, Fjj. And we can do this because of Markov. It doesn't depend on history. Once you hit where you want to hit, you can just condition it from there. So this will be Fij, Fjj whole power k minus 1. So these are the basic definitions that we want to learn before recurrences. This thing. So now we go and state the definition of recurrent Markov chain. A recurrent state in a Markov chain. A state I of a Markov chain is recurrent if probability that conditioned on I xn equal to I is equal to 1. That is Fii is equal to 1. If Fii is less than 1, then we call this as transient state. So what does this mean is the probability of you hitting I if you start from I is 1. So if you almost surely can hit I if you start I, that means you come back to I, then it is known as recurrent state. So, and if it is less than 1, then it is known as a transient state. So now we'll do a, I hope the definitions are clear. So now we'll do a proof on the recurrent state theorem. So the theorem states that state I is recurrent if and only if probability I condition on starting at I, ni equal to infinity equal to 1. If and only if summation n equal to 1 to infinity pi n equal to infinity. So these both are equivalent. So starting from I, the probability that you will hit I infinitely often or infinite number of times, almost surely, is the same as saying that the nth step, the summations of all the n step probabilities from I to I goes to infinity. Next is state I is transient. If and only if equal to infinity equal to 0, and only if. So these both are also equivalent. So if a state is recurrent, that means these both are equivalent and these both are equivalent. Similarly, less than infinity. So we'll do a short proof for this. So by continuity of probabilities, we can say that probability that condition on you're starting at I, state I, number of times you have hit I is infinity. This event is equal to limit k tends to infinity equal to a. Number of times you have hit is greater than or equal to. So we know that this probability is just limit k tends to infinity. So what does this give us? The probability that it hits I at least k number of times, at least one number of times, two number of times, three number of times. As you increase the number of times, you will reach, as you keep on increasing k, the number of times you hit I would increase to infinity. So the probability that you start at I and you hit I again infinitely often or infinite many number of times is same as saying that it is the limiting probability of um, you hitting I k number of times where the limit of k goes to infinity. So we know the probability for this as pi I whole power k. Now we know this is 1 if fi I equal to 1. If it is 0, if it is anything other than 1, it is 0. So fi I is less than 1. So what we have showed is okay. So if fi I equal to 1, that implies that okay. So from here, if fi I equals 1, which means that state is recurrent. So state recurrent in sorry. So now if state is recurrent, that implies probability of I n I equal to infinity equal to 1. If state is transient, it implies probability of I n I equal to infinity equal to 0. So we have showed these two. Okay. Oh, so next we'll show that uh, okay. So now we need to understand what this term is. Summation n equal to 1 to infinity pii n, which is equal to summation n equal to 1 to infinity pi xn equal to I. Now it's not that the nth step is I. So we have seen in the fundamental of probabilities that the summation of probabilities is basically the probabilities can be written as expectation of indicator random variable. Now the indicator random variable is if xn is I or not. And expectation I and from linearity. So here to there we are using linearity of expectation. Indicator xn equal to I. Now this is expectation number of times you are just counting the number of times here. So this will be one if nth time is if nth time you hit the ith state or not. It will be zero if you don't hit the ith state. So you are basically counting the number of times that you hit I. This is equal to so this we know it as FII. So this we can write it as where this is equal to infinity if FII equal to 1. FI is a probability, so it can't be more than 1. But if it even if it is more than 1, it goes to infinity because this summation would diverge. But if it is FII by 1 minus FII, which is less than infinity, if FII is less than. So again, coming back to that recurrence definition. So what you've shown is, um, yeah, we have shown if recurrent, then this is infinity. And if transient, then this is less than infinity. Okay, so this is just one part of the proof for the recurrent state theorem, where you can see that we have proved that if state I is recurrent, then probability that you'll hit I infinitely often, given that you're starting at I, is 1. And If state is recurrent, then the summation of PII nth step transition probabilities, they are the summation is infinity. If I is transient, the summation is finite. And also if state is transient, then uh, probability that you'll hit I infinite number of times starting from I is equal to zero. So now we'll do an example. So first, let me define a discrete Markov chain. To define the discrete Markov chain, we'll need the state space, the transit probability matrix, and the initial. Okay, so first the state space. So the state space given by 1, 2, 3, 4. There are 4 states, and the state transition probability matrix is given by. So it will be 4 by 4 matrix. One zero zero zero. 1 by 4, 1 by 4, 1 by 2, 0, 0, 0, 2 by 5, 3 by 5, 0, 0, 1 by 3, 2 by 3. We will also draw the state transition matrix, state transition diagram. So if you are at 1, with probability 1, you go to 1, not anywhere else. If you are at 2, with probability 1 by 2, you go at 1 by 4, you go to 1, with probability 1 by 4, you go to 2, probability 1 by 4, you go to 3, 1 by 2, you go to 3. If you are at 3, probability 2 by 5, you go to 3, and with probability 3 by 5, you go to 4. If you are at 4, with probability 1 by 3, you go to 3, with probability 2 by 3. So here we can see that 4 and 3 are communicating class. 2 is a communicating class on itself. 1 is a communicating class on itself. So we want to find what are the different FIG values. So first we'll see